welcome back to Stelzer Science. I'm in a little bit of a different setup today. My work desk right now is being occupied by a whole bunch of unopened mail that I don't want to deal with. So rather than face my problems head on, I decided to let's just move it to the dining room. So we're in my dining room right now, and out there is my lanai with my carnival lights up. So today we are, or whenever you're watching this, in this video, we're going to do the multiple choice review for the AP Chemistry exam. And then the next video we'll be doing the FRQ for the AP Chemistry exam. Let's go ahead and get into it. Okay. Let's do a little green today. Okay, 14 questions, minute and a half per question. We know the drill. Let's get into it. All right, question 1. When a student adds 30 milliliters of 1 molar hydrochloric acid to 56 milliliters of powdered iron, a reaction occurs according to the equation above. When the reaction is complete at 273 Kelvin and 1 atm, which of the following is true? So right away, I see that we have information about one reactant, and then we have information about another reactant. So this kind of clues me into that this is a limiting reactant problem. This is a stoichiometry problem. What we have to do is we have to compare how much reactant we have so we can see how much the reaction progressed. HCl is in excess, 0.1 mole of HCl remains. HCl is in excess, 0.02 moles of HCl remains. 0.015 moles of FeCl2 has been produced. 0.22 liters of H2 has been produced. All right, this question is kind of a mean one because, okay, we have two quantities of reactants. That is what clues me into that we're going to need to do stoichiometry, and we're going to need to figure out what is the limiting reactant. But there is no nice simple way to solve this problem other than we just have to go through and check if each answer choice is true or not true one by one. So let's go ahead and do that. I guess no time like the present to get started. In actuality, I would probably skip a question like this on an exam and come back to it later on. All right. We have quantities of both, so we need to get to moles of both so we can compare better. So for the HCl, we're going to do molarity equals moles over liters. The molarity is 1. We're solving for moles. We have 0.03 liters, which means we have 0.03 moles of HCl. For the iron, we have 0.56 grams of iron. To get to moles, it's just dividing by molar mass. And the molar mass of iron is from your periodic table. I happen to memorize it, have that memorized. It's 55.85 grams per 1 mole. So 0.56 divided by 55.85 is 0.01 moles of iron. So 0.03 moles of hydrochloric acid, 0.01 moles of iron. I can tell that the iron here is going to be the limiting reactant, not necessarily just because it has less, but because it has less than half the amount. So iron and hydrochloric acid will react in a 1-to-2 ratio, but we have more than 2 times the amount of hydrochloric acid, so therefore iron is the limiting reactant. Every one of these questions has to be based off the limiting reactant from now on. So let's start off by finding out, to address A and B, let's find out how much hydrochloric acid was used in our iron with this amount of iron. For every 1 mole of iron that reacts, we get 2 moles of HCl, which means we use 0.02 moles of HCl. So HCl is in excess. We used 0.02, we started off with 0.03, so we should have 0.01, but that's neither of these answer choices, so it's not A and B. This one says 0.1, this one says 0.02, neither are the correct number. For C, 0.015 moles of iron to chloride has been produced. Let's go ahead and check that. Let's start off with 0.01 moles of iron. For every 1 mole of iron, it's 1 mole of iron to chloride. So it's just 0.01 moles of iron 2 chloride. That's not the correct amount. This question says 0.015. So just by process of elimination, I know it has to be D, but let's go ahead and check 0.01 moles of iron. And for every 1 mole of iron, I'm in the way, there's 1 mole of H2. And then it is at STP, so I'm going to use the shortcut instead of going to Pivnert to find out the volume. If it wasn't at STP, we can plug everything into PV equals nRT. We have R, we always have R, we have temperature, we have the pressure, we can find the moles, and we would solve for volume. But we can just use for every 1 mole, it's 22.4 liters. And if we do that out, we get that it's 0.224 liters of H2, which is that number rounded to sig figs. All right, that was a long question. Test taking strategy. If you can foresee that a question is going to take you a long time to do, don't linger on it. Move on. Don't let one question tank 4 questions down the line. Continue the test, come back to it. So the answer to that one is D. Also, just FYI, I don't have the key with me, so I can't double check my answers. If I make a mistake in either of these videos, I guess I'll just like completely shut down the YouTube channel. I think I'll be so embarrassed. I'll just retire. All right. 2. A 0.50 gram sample of magnesium was placed in a solution of hydrochloric acid where it reacted completely and a gas was produced. Which of the following equations best represents the reacting species in the reactant described above? So when I see this term reactant species, this just comes from experience. That usually means net ionic. What a net ionic equation is, it is an equation that only shows the things that are undergoing or that are active participants in the reaction. Because if we think about how we make a net ionic equation, first we separate into ions and we cancel out spectator ions. Spectator ions are the ions that are just floating aimlessly that are not participating in the reaction. So if we want to show a reaction of just the reacting species, it should be a net ionic. So again, we just have to look through each of these. We combine solid magnesium with hydrochloric acid and a gas is produced. Those are our hints. Let's see which of these makes the most sense. So magnesium plus 2H plus yields magnesium 2 plus H2 gas. That one looks like it could be right. B, magnesium plus hydrochloric acid yields magnesium chloride plus hydrogen gas. This is not an ionic equation, and this one is not correct because it's not balanced. We have 1 H on this side but 2 H's on this side, and we also have 1 Cl on this side but 2 Cl's on this side. It also doesn't break up the magnesium chloride. Not that it necessarily needs to, but this question is kind of implying net ionic, but this was wrong because it's just not balanced. C, magnesium solid plus 2 HCl yields magnesium chloride solid plus 2 H plus. 2 reasons why this one's wrong. Reason numero uno is because this 2H plus gas is not a thing. That is not hydrogen gas. Hydrogen gas should be H2. Reason number 2 is because magnesium chloride is not a solid. Magnesium chloride is soluble. Chlorides are usually soluble. The exceptions for halogens is PMS, and it is not lead, mercury, or silver. So magnesium chloride is soluble. It's not C. D, we have magnesium solid plus 2 hydrochloric acid yields magnesium 2 plus Cl2 plus H2. I'm in between A and D, and the answer I'm going to choose is A. I think A does a better job of showing the reactant species. D does not break up hydrochloric acid into 2H plus and 2Cl minus, even though it did the same for magnesium on the other side. Also, magnesium is not really doing anything in this reaction. It's just going from magnesium to magnesium 2 plus. It's just giving away 2 electrons and then letting HCl become Cl gas and H2 gas. I think A is way more likely. A is the correct answer. Even though there's no Cl that appears in A, Cl is a spectator ion, so it would have gotten canceled out. All right, two tough ones to start off. Let's go to 3. How many electrons are transferred in the reaction represented by the balanced equation above? So redox reaction, to find out how many electrons are transferred, we have to calculate oxidation numbers. MnO4 minus. O is -2. We have a total minus charge of -8, which means this one manganese needs to be +7 to get the -1 charge. It's kind of hard to see on this paper. Br minus is just -1. Ions keep the charge of their ion. Same thing with this H plus, +1. Same thing with this manganese 2 plus, +2. Br2 is neutral, so it turns into 0. And then H2O, we have -2 for oxygen, +1 for hydrogen, which is always going to be the case with water. To find out how many electrons are transferred, we don't need to identify what's being oxidized and what's being reduced, but we just need to look at one of the two things. So what's changing? I think I can see that the bromine is changing. So bromine is going from -1 on the left side to 0 on the right side. However, oxidation numbers are per individual atom. This process is happening. This is 1 electron being transferred. However, this process is happening 10 times. I guess the electron goes the other way. But you get the idea. It's 1 electron being lost. However, because we have 10 bromines, that happens 10 different times. So therefore the answer is 10. If we were to balance this reaction, we would need 10 electrons on this side to balance out the charges. We can also do this based off the manganese. So we have 2 Mn, and then it's a +7 over here, and it turns into 2 Mn2 plus with a +2 over here. So we have a change of 5 electrons. We'll put this down. We have a change of 5 electrons. We are gaining 5 electrons. But since we have 2 manganese, those 5 electrons being transferred happens twice, so it's 10 total electrons being transferred. If we wanted to balance this reaction, it would be like that. All right, moving on to 4. The particle diagram represents an aqueous solution of a weak monoprotic acid. A monoprotic acid is just an acid that's hydrogen bonded to something else. For example, hydrochloric acid. Or it can be like hydrofluoric acid, something like that. The white crystals represent H atoms. Circles, I don't know why I read crystals. The right circles represent H atoms. Which of the following shows the species that act as the Bronston-Lowry base and its conjugate acid? So we're looking for a base and its conjugate acid. A base is a proton acceptor. Instead of proton, I'll put an H plus acceptor. The conjugate acid is what results from accepting. Conjugate acid base pairs, they exist in pairs. If an acid is something that donates a proton, the conjugate base is what the acid becomes after it donates the proton. If a base is a proton acceptor, something that accepts a proton, the conjugate acid is the thing that the base becomes after it accepted that proton. So since we know that the H's are the circles, we're looking for something that has 1 or 0 circles, and then it's paired with something that has 1 extra circle, because we're trying to signify something that has a certain amount of hydrogens, and then its conjugate acid will be something that has 1 more hydrogen because it accepted a hydrogen. So the only one that does that is D here. We go from 2 H's to 3 H's, signifying we added an H. Base and conjugate acid. A student mixes 20 grams of white potassium chloride crystals with distilled water in a beaker. After the mixture was stirred, no crystals are visible and the solution is clear. Okay, now we got crystals. Maybe I was just reading the next problem. After several days, all the water evaporates and white crystals are found in the beaker. Which of the following pieces of experimental evidence would best help the student to confirm that a new compound has not been made and that only a physical change occurred? By physical change, in this scenario, we're talking about just dissolving. How can this student, so the student has water and they put a whole bunch of potassium chloride crystals into water and stirred, and all the potassium crystals disappeared. Potassium chloride crystals disappeared. When the water evaporated, the crystals came back. How can we confirm that no reaction took place and that all that happened was dissolving? This happened, so B is not true. They are no longer visible after they're mixing with water. Just because there's a temperature change doesn't mean that it is a chemical reaction. A temperature change is evidence of a chemical reaction, but it doesn't necessarily prove that it didn't dissolve. Calcium chloride, we've worked with it a few times. It produces heat when it dissolves, but we can still get that calcium chloride back. Again with A, just because there is no color change doesn't mean that a reaction didn't occur. We can have reactions that don't change color. The answer is D. When the water evaporates, if we get the same mass of potassium chloride back, that lets us know that none of the potassium chloride reacted, it just dissolved. And then after it gets evaporated, it comes back. All right, 6 through 8, take a look at all of these reactions. And 6, we're looking for the reaction in which a single species is both oxidized and reduced. All right, so what it means by a single species being both oxidized and reduced, it means that, let's say I have, carbon, and carbon is +2 on this side oxidation number. That means on this side, it turned into a +4 and like a 0, or let's say a +1. Meaning it got oxidized, it lost electrons, and it got reduced, it gained electrons. So which one of those do this? So let's check A. Oxygen is 0 over here. It's -2 in this, and then it's -2 in this. So it's not A. Oxygen is the only other thing that appears in 2 other products on this side. Let's see what else. E looks like it can work. As a matter of fact, I've seen this reaction before, so I know E is correct. So oxygen is 0 on this side, it's -2 on this side, and in hydrogen peroxide, oxygen is -1. That is the one exception for oxygen in covalent compounds. So it was both oxidized, it lost an electron, going from -1 to 0 in oxygen gas, and it was reduced. It gained an electron going from -1 to -2 from hydrogen peroxide to water. So the answer is E. The reaction between a Bronsted-Lowry acid and a Bronsted-Lowry base. So for 7, we're just looking at which of these had a proton donor and a proton acceptor. B is the one that looks correct here. We have H3O, our proton donor, acetate, our proton acceptor. Acetate turns into acetic acid, H3O plus turns into H2O. So B is the answer for that one. A precipitation reaction. So we're looking for a solid being formed out of not solid, and there's only one that does that. It's D. The calcium ion plus the sulfate ion yields the calcium sulfate. The half reactions for oxidation reduction reaction between aluminum and zinc, 2+, are represented above. Based on the half reactions, what is the coefficient for aluminum in the equation for the oxidation reduction reaction when it's balanced to the smallest whole number ratio? Okay, so with balancing redox reactions, the key is to get the electrons to balance out. We want the electrons to be equal, so when we add the reaction back together, electrons will cancel out. They'll be the same on both sides. The way to do this is we're going to multiply this aluminum half reaction by 2 and this zinc half reaction by 3 so that both the electrons turn into 6e minus. That's the lowest common factor. I don't remember the math term. We want to get them both the same number, and the best way to do that is to get them both to 6. We don't need to add the reaction because it's just asking what's the coefficient in front of the aluminum, and that's going to be 2 because we're multiplying this reaction by 2. So B. The diagrams above represent solutes present in two different dilute aqueous solutions before they were mixed. So we have sodium chloride, and then we have silver nitrate. When the solutions were combined, a precipitation reaction took place. Which of the diagrams below is the best particulate representation of the mixture after the precipitation reaction occurs? So first off, we don't have a reaction here, but we know there has to be a precipitate. We're given that this is a precipitation reaction. So what's going to be the precipitate when we add these two? The precipitate is the thing that's going to be not soluble. It's going to be silver with chloride. Sodium with nitrate is going to be soluble. We know that silver nitrate is soluble. We know that silver chloride is soluble. Those are our reactants. Has to be silver chloride. So right off the get-go, we're going to not pick A and we're going to not pick C because they don't depict a precipitate of silver chloride. D and B do. We have silver chloride down here, and we have silver chloride as a solid in this one as well. Which one is correct then comes down to how do we treat the sodium nitrate. Do we keep the sodium nitrates together, or do we break the sodium nitrates up into individual ions? And the answer to this is D. When something is aqueous, when we have aqueous sodium nitrate, what we have really is Na plus and NO3 minus. This is a white lie. Sodium nitrate is not actually present. What is present is sodium ions and nitrate ions dissolved in the solution. That's why when we do a net ionic, we break them apart and we cancel out spectator ions. If we were to make a reaction with this, sodium and nitrate would be the spectator ions and they would cancel out. The net ionic would be silver plus chloride yields silver chloride. That's the actual reaction that's happening. All right, next one. According to the reaction represented above, how many grams of aluminum, molar mass of 27, are necessary to produce 0.5 moles of hydrogen gas at 25 degrees Celsius and 1 atm? All right, this one looks like a stoichiometry problem. And it is a stoichiometry problem. So first off, they give us temperature and pressure, but we're not actually going to use that because we already have moles of hydrogen gas and we want to find out grams of aluminum. We don't need to use Pivnert to get to moles because they give us moles already. I can see them not giving us moles and maybe giving us like a volume, but let's start off with what we have. We have 0.5 moles of H2. For every 3 moles of H2, there's 2 moles of Al. And then for every 1 mole of Al, we're given that it has a molar mass of 27 grams. And we get 0.5 times 2 times 27 divided by 3. We get 9.0 grams of aluminum, which is B. All right, 12. A sample of C4H10 is placed in a rigid vessel with a movable piston. The volume of the gas is reduced by moving the piston downwards. So we're taking this piston. This is what happens in your car. There's gas in here. Ooh. And then we take that piston and we push it down. The volume greatly decreases and the gas gets compressed. According to Boyle's law, P1V1 equals P2V2. As volume goes down, pressure should go up to balance out. I guess I should have done that on the V2 side. and we're given the pressure of the gas versus its volume. Which of the following best accounts for the pressure in the vessel remaining constant as the volume decreases below 0.21 liters? Okay, conceptually it's not hard to figure out what's going on here. What is difficult is this is a graph you haven't seen before. It's kind of a weird graph because probably the first way you read this is not the way you're supposed to read this. We have a piston, and as this piston is being compressed. As the piston is compressed, we expect the volume to go down, so therefore we expect the pressure to go up. I'm about to lose battery. No, don't do it again to me. Don't do it again. Saved. We didn't lose power again. Okay, what I was saying is, so I'm lagging. What I was saying is pressure goes down, volume goes down, pressure goes up. So you might be reading something that's not here. This is not pressure versus time. If this were pressure versus time, we would see that pressure begin to increase with time. This is pressure versus volume. What we're saying here is as the volume gets bigger, as we move this way on the x-axis, the volume gets bigger, which means the pressure goes down. This graph is reading correctly. But what we're meant to read is why, when we get to a volume of 0.21, when we keep decreasing it, so what I'm saying is the graph is actually read this way. This direction signifies the piston moving. When we get to 0.21, why does the pressure stop changing? Well, Boyle's law says the pressure should be going up, but it doesn't. So which of these can explain why the pressure stops changing? Is it because the density of the C4H10 gas increases? No, that wouldn't explain it. That would explain a higher pressure. The surface area of the interior vessel decreases. That is true, but that would also lead to a higher pressure. We have a lower surface area, which means particles are hitting the walls more frequently. The temperature decreases. That's just false because the question says the temperature is maintained. The only thing that explains that is D. Some of the gas condenses into liquid, and liquid is not impacting this pressure. If we condense some of this gas to liquid, that means we're losing gas. We have just less gas in there, so that means the pressure the pressure can remain constant because as we decrease volume, some of the gas gets condensed. Basically, the pressure maxed out, and any other increase in volume means gas gets turned to liquid. Tough one. All right, last two questions. A student was studying physical and chemical changes. Wow, sounds like a fun time. The student carried out some procedures in the laboratory and recorded observations. For one of the procedures, the student concluded that a physical change took place, but not a chemical change. Which of the following could have been the result of this procedure? So we're looking for something that is a physical change, but not a chemical change. A cube of metal was changed into a flat sheet of metal. I think that checks out. When two liquids at room temperature were combined in a beaker, the beaker became hot. That could be a chemical change, so even though that could also be just something dissolving, that also could be a chemical change. When two clear liquids were combined, the resulting mixture was cloudy. We know that that's a chemical change. That's a precipitate forming. When a colorless liquid was added to a blue liquid, the resulting solution was yellow. That's also evidence of a chemical change. The only one of these answer choices that guarantees no chemical change is just the making a cube sheet into a flat sheet. There's no chemical reaction taking place. We're not changing the chemical composition of this sheet. Maybe B and D don't necessarily mean chemical reaction, or actually D would mean a chemical reaction took place. But A for sure, there's no chemical reaction there. Gaseous hydrogen and gaseous chlorine can react to form hydrogen chloride gas at the reaction represented by the following equation. It does not give you the equation. I remember this question. You're supposed to be given the equation. The equation for this reaction is H2 plus Cl2 yields 2HCl. That is, that's my bad. That was a my bad from last year, and I gave them the equation on their test last year, like on the board. So you're supposed to have that. My bad. The diagram shows the particulate representation for the samples of gases and separated by a barrier. After the reaction barrier is removed, the gases react. Which of the following diagrams best represents the mixture if the reaction goes to completion? All right, H2 and Cl2 react in a 1-to-1 ratio. I have 4 here, 4 H2s. I have 5 Cl2s, so we should get, if I have 4 of these, 5 of these, I should get 8 of these with 1 of these remaining. So I should, it's C. So 1, 2, 3, 4, 4, 5, 6, 7, 8. And then 1 chlorine gas remaining. I did that math in my head, but we can more thoroughly do this one together. So we have 4 H2s and 5 Cl2s, and we start off with none of these. If we run the reaction once, we use up 1, we use up 1, we create 2. Let's run it again. Use up 1, use up 1, create 2. Use up 1, use up 1, create 2. Use up 1, use up 1, create 2. We know we have run out of a reactant, so we cannot progress this reaction more. We have 1 Cl2 remaining. We have 8 HCls. All right, that concludes the multiple choice. Yeah, I'll see you guys in the FRQ. Let's close out. Eventually I'm going to get good at ending the video promptly, but I'm not. All right, see ya.